Hall effect. This effect was observed by the scientist E. H. Hall in 1879, and so it is called Hall effect. The Hall effect is observed in both semiconductor as well as in the conductor. So let us see what is this Hall effect. According to this effect, conductor or semiconductor carrying a current I is placed in transverse magnetic field. Transverse magnetic field means the direction of the magnetic field and the current is perpendicular to each other. Then a potential difference VH is developed in a direction perpendicular to both direction of current and magnetic field. It means that the electric field is developed in a direction perpendicular to both the direction of current and direction of magnetic field. That is Hall effect. Let us consider, in this case, we are talking about the semiconductor, so we will consider a slice of semiconductor whose width is d and the thickness is t. So in this case, consider a slice of semiconductor of width small d and thickness small t. See, this is the sample of, this is a slice of semiconductor. As you can see, its width is d over here and the thickness is t. This is the thickness t. And you can see that the current is flowing in this direction. This is current I. But electrons are moving in opposite direction. So here you can see that the current I is flowing through semiconductor from right, from left to right. And electrons are moving from right to left. So this is in, there is no magnetic field applied here. Only the current I is flowing through the semiconductor, and this flow of electrons is parallel to the top and bottom surface of the semiconductor. Okay, there is no magnetic field applied here. So in absence of magnetic field, electrons flow parallel to top and bottom surface, as shown in this diagram. As you can see that the electrons are moving from right to left, which is parallel to the top and bottom surface. What happens when magnetic field is applied? On application of magnetic field, this magnetic field we have to apply in a direction perpendicular to the direction of current. So we are going to apply magnetic field which would be perpendicular to this paper. As you can see here, the current is moving from left to right. And then we are going to apply the magnetic field which will be perpendicular to this paper. So magnetic field is going through this paper. That diagram is shown over here. As you can see here, this is the magnetic field B shown by this arrow lines. This magnetic field is perpendicular to this paper. It is going through this page. And the current was earlier moving from left to right. So magnetic field we have applied perpendicular to the direction of the current. Then when magnetic field is applied, then the electrons which were moving parallel to the top and bottom surface, they will experience Lorentz force. So what happens then? Electrons experience sideway deflection due to Lorentz force. This is according to Fleming's left hand rule. The electrons will feel a force towards the bottom of the surface. That means electrons are deflected towards the bottom of the surface as shown in this diagram. Lorentz force will act in this direction, and that Lorentz force is, say, Fl. This Lorentz force is acting on the electrons. So these electrons experience a sideway deflection. That means electrons are moving towards the bottom surface. So according to this Fleming left hand rule, electrons deflected towards bottom surface, as Lorentz force is acting, as I shown in the diagram, towards the bottom. Direction of Lorentz force is from top surface to bottom surface, and so the electrons are deflected towards the bottom surface. Because of that, what happens? Bottom surface develop negative charge. There are more electrons on the bottom surface. So with respect to the top surface, this bottom surface develop a negative charge, and equal amount of positive charge is developed on the top surface, shown over here. Because of it, bottom surface develops negative charge and equal amount of positive charge developed on the top surface. It means that electric field is produced between the top and bottom surface. Electric field is produced between top and bottom surface called Hall electric field, which is denoted by E suffix capital H. That is Hall electric field. And potential difference developed between top and bottom surface is called Hall potential, which is denoted by V suffix capital H. Now, as I said that this electric field is developed between the top and bottom surface, so there would be electric force acting against the Lorentz force. So, direction of electric force would be this, in opposite to Lorentz force. And this force opposes further piling of electrons at the bottom surface. See, when magnetic field is applied due to Lorentz force, electrons are deflected towards the bottom surface. Then electric field is developed between the top and bottom surface. This electric field opposes the flow of electrons towards the bottom surface. Let me write that. Electric field opposes piling of electrons on bottom surface. It is opposing the accumulation of electrons on the bottom surface. So the electric force acts in the direction opposite to Lorentz force. So then equilibrium condition is reached Equilibrium condition means Lorentz force is equals to electric force. So when Lorentz force equals to electric force, equilibrium condition is reached in 10 to power minus 14 seconds. When Lorentz force balanced by electric force. So and they are acting in opposite direction to each other. and so the equilibrium condition is reached. So when the equilibrium condition is reached, then again electrons flow. In this case, as we can see that how electrons are flowing. Because of Lorentz force, all electrons are piled or accumulated on the bottom surface, and then they will move in this direction. So this direction of electron flow is not parallel to the top and bottom surface. But at equilibrium condition, this Lorentz force is equals to electric force. When Lorentz force is equals to the electric force, equilibrium condition is reached. And at the equilibrium condition, this accumulation of the electron stops. And in that case, again, electrons will start moving parallel to top and bottom surface. Let me write that. At equilibrium condition, electron starts moving parallel to top and bottom surface. Again, let us see that in the diagram as I shown over here. The equilibrium condition is reached in this case, and when equilibrium condition is reached, again you can see here electrons start flowing parallel to the top and bottom surface, where the top surface is having now positive charge, bottom surface is having negative charge, and across this there is a potential difference VH and electric field EH. So as we see that, what happens, let's see what happens at equilibrium condition. At equilibrium condition, this Lorentz force FL is equals to electric force, that is Fe. But this Fe, that is electric force, is nothing but E into Vh upon d. This small d is the width of the semiconductor slice. Vh is the Hall potential, E is the charge. Let's name this equation as equation 1. And the Lorentz force Fl is given by the equation E v v d. In this case, E is the charge, B is the magnetic field, and Vd is the drift velocity. Let's say that is equation 2. However, current is given by the relation I is equals to NAEVD. Vd is the drift velocity, E is the charge, A is the cross-sectional area of the semiconductor, and N in this case is number of electrons. You also know that the current density is denoted by letters J, which is equals to I upon A. So let us substitute the value of I in this equation. Therefore, J is equals to NAEVD divided by A, and that is equals to NEVD. Further, we can simplify as, and let us find Vd. So Vd is equals to J upon N. and this is our equation 3. Substitute equation 3 in equation 1, not equation 1, equation 2. Vd we will substitute in this equation of Lorentz force. Then we get Lorentz force Fl is equals to E B into Vd, which is J upon Ne, and that is equals to Bj by N, which is Lorentz force. And this is equation 4. So we got equation 4 for Lorentz force and equation 1 for electric force. So let us equate this at equilibrium condition. So we have Fl equals to Fe, and therefore Fl is Bj upon N and Fe is he Vh upon D from equation 1 and 4. Let us simplify this further and write the Hall potential. So Hall potential, which is Vh, and that is equals to Bjd upon Ne. Let's say this is equation 5. This we can further write as Vh is equals to Vid upon NEA. This is equation 6. Since J is equals to I upon E. We know that the thickness of the sample is T here. So if T is thickness of semiconductor, then cross-sectional area is A is equals to dt. D is the width, T is the thickness. So cross-sectional area is dt. Then equation 6 is becomes Vh is equals to this Bid upon NEA. Instead of A, it is dt. So Ne dt. So this d cancels and you get Vh is equals to Bi upon Net. This is equation 7. What we have to find is the Hall coefficient, and the definition of Hall coefficient is Hall coefficient is denoted by R suffix H, and its definition is Hall field per unit current density per unit magnetic field. That is called the Hall coefficient. It means this RH is equals to Hall field is denoted by the letter EH, divided by per unit current density is J, per unit magnetic field, that is B. That is equals to VH upon EH is VH by D. So this VH upon JBD, since EH is equals to VH upon D. And let's say this is equation 8. Then let us substitute the value of VH. VH is, as per equation 5, let us write this. Substitute equation 5 in equation 8. Equation 5 is given over here. Equation 5 is BJD by NE. VH is BJD by NE. So RH is equals to VH, which is BJD upon NE into 1 upon JBD. That is nothing but this RH is equals to 1 upon NE, and this is equation 9. As these terms cancels, we got RH, that is Hall coefficient, is equals to 1 upon Ne, where N is the number of charge carriers and E is the charge on the electrons. We also have here in this case this VH is equals to Bi upon NET as per equation 7. See, the equation 7 is VH is equals to Bi upon NET. That means 1 upon Ne into Bi upon T. And this 1 by Ne is nothing but RH. So RH Bi upon T is equals to VH. Since RH is equals to 1 by Ne. From this equation, we can find again RH value of RH, which is VHT upon Bi. So RH we can find using this equation, equation 9, as well as equation number 10. And the value of RH is negative for N types semiconductor. RH is negative for N type semiconductor. And obviously it is a positive for P type semiconductor.